Hello and welcome to AIT 1102 Fluid Power Distribution. My name is Matt Luckett and I will be the instructor for this course. As we go through this material, there are 6 lessons in this class, and each lesson will have a presentation much like this one. These presentations are introductions to the lesson and it is not intended to be the entire lesson. This presentation is to provide some baseline or foundational material for you to build on before you actually get into the textbook material, and to hopefully give you a better understanding as you progress through. So to get started, our first lesson here is on hydraulic pumps, and this presentation we're going to describe what a hydraulic pump is. We're going to identify hydraulic pump categories. We're going to describe hydraulic pump ratings. We're going to describe fixed and variable displacement hydraulic pumps. We're going to identify schematic symbols, and then finally we're going to identify some failures or causes for failures of hydraulic pumps. So for the duration of this course, we're going to be working off this schematic here, and as we progress through the course, you'll gain a better understanding of what's going on here. But we're going to break it down, and for this first lesson, we're going to focus on one area of this schematic, and that's this part right here. This is the hydraulic pump on this schematic. So what is a hydraulic pump? A hydraulic pump is a mechanical device that converts mechanical energy into hydraulic energy. And in 1003, AIT 1003, you learn the foundational, or you learn basic information about hydraulic and pneumatic systems. And for this part, we're going to discuss hydraulics, and towards the end of the class, we'll get into pneumatics. So by definition, a hydraulic pump converts mechanical energy into hydraulic energy. So by that definition, we have to have a source of mechanical energy. So there's 2 different types that you'll find typically in an industrial environment. These sources of mechanical energy are also known as a prime mover for a hydraulic pump. The first type is electric motor. You've seen these in several different locations. You've probably worked with some in your labs here in the AIT lab. But excuse me. But basically, you have an electric motor. The pump is attached to the shaft, and as it spins the pump and generates the flow from a hydraulic pump. The second type of prime mover is an internal combustion engine. It can be gas or diesel. This is just an example. We've got an engine here, and through this shaft, and then the hydraulic unit's back here behind there where you're spinning your pump. So moving along, we have 2 different types of pump categories as well. We have non-positive displacement pumps or dynamic pumps, and then we also have positive displacement pumps. And there's a pretty significant difference. We'll look at the dynamic pump first. So the dynamic pump is a velocity pump in which kinetic energy is added to the fluid by increasing the flow velocity. So basically what that's doing is we've got an impeller or a fan inducing flow into the current, into the fluid. And these types of pumps can be deadheaded without damage, and I'm going to just discuss that a little bit more here in just a minute. So here's an example of a dynamic pump. You see that there's no seals, no tight clearances. This is much like a pump you might find on a pool pump, that you've got a housing here, and you've got fluid coming into the end here, and this impeller is just spinning with these blades, and it slings the fluid outward, and it follows this outlet here, and it just creates fluid flow. So with this type of fluid flow, you're not going to generate a lot of pressure, but it's all about moving the fluid. And the second part of that previous slide, when I was talking about deadheading, what deadheading is basically you're blocking the flow. So if I cover this up and deadheaded this pump where I'm not allowing any fluid to flow, this impeller would continue to spin, and it would not tear anything up. It would just sit there and spin within the fluid, and it'd be generating heat. But given that there's no tight tolerances in here, and it's much like think of it like a box fan that you use at home. It's sitting there spinning, it's moving the air, but it's not creating a lot of pressure. And if you block the front or the back of that fan, or the front of it, to stop all the airflow, you'd be deadheading that fan, and it would not tear anything up. The blade would sit there and continue to spin. Positive displacement pumps are a little different. They're a pump that moves fluid flow, removes fluid by repeatedly enclosing a fixed volume, moving it mechanically through the system. Pumping action is cyclic and can be driven by pistons, screws, gears, rollers, diaphragms, or vanes. And deadheading, these types of pumps will cause damage. So basically, if you read the description here, it says we're enclosing a fixed volume. So within these pumps, you have tight seals, you have tight tolerances, and once it picks up the volume of fluid to pump into the outlet of the pump, that is a sealed volume. And if I try to block that pump, that sealed volume, I mean, it's got to go somewhere. So if you block it and your pump's still turning, you'll damage the pump because that's like a solid volume that is trying to move. So as a positive displacement pump, we're going to talk about 3 different types here. The first type is a vane type. And here's just an example of what a vane type pump might look like. And here's a graphic representation. Basically, I've got this center part in here encloses the vanes. These parts here are the vanes. So as your fluid comes in here, this vane rotor is spinning this way. So you can see that it's picking up a volume of fluid. And as it rotates around here, we start closing the area down, which is forcing the fluid out the outlet here. And so these vanes, see that they're sealed to the outer part of the housing. So once it picks up this volume of fluid, as it's continuing to turn, it has to kick this fluid out the outlet of the pump. And if you look close, you can see that these vanes have got like a slight taper on the end here. That's very important. If you ever rebuild one of these pumps, you want to make absolutely sure you get those vanes with the leading edge that goes out against the outer housing. If you take this vane and you spin it around where the clearance part is down here facing the direction of flow, as it tries to build pressure, it'll actually slam that vane back down into the rotor, and you'll know right away if you put one of those vanes in backwards because it becomes very loud. It's just like a really loud hammering noise. So, but like I said, this is the first type of displacement pump we're going to talk about. It's a vane. And you can see what it looks like. We've got a center rotor with the vanes that slide in and out, and we're picking up fluid and putting it out the outlet. The next type of pump is a gear pump. It is also a positive displacement pump. And here's just an example of what one might look like. And here's another graphic example of a gear pump. And so basically what you have with a gear pump is your prime mover is attached to one of the gears here. So this would be your driven gear, and this is your idle gear. So just by this one spinning and meshing with this one, it causes this one to turn. So the fluid flow in a gear pump flows around the outside, and as here's your sealed volumes as you go around the gears, and it'll move this up here, and as it gets up to this area, it pushes the fluid out your outlet, and you have some minor leakage here in the middle where some fluid may come back into your inlet, but it's not enough to create an issue with the pump. So with these tight seals, I said you'll see you'll get a little bit of leakage coming back into the inlet side, but for the most part, the fluid that you pick up here is pushed right outside, right to the outlet. The next type of pump, a little more complicated, is the piston pump. So here's what one might look like if you found one in the field. Here's a graphical representation. So your prime mover attaches back here to this shaft, and you're spinning this housing, or this plate here, that has the pistons on it. And then up here you have a housing with your cylinders, and you have your inlet and your outlet. So as this plate spins, you notice it's on an angle. So as this plate spins, it's like pulling a syringe. These pistons start pulling out and draw fluid in, and as it rotates around, the other side of the piston the other side of the plate, it actually pushes the piston back out like you're pushing the syringe out to discharge the fluid. So this back here, this is called a swash plate, and we're going to talk a little bit more about the advantages of using this type of pump here, what you can do with it. But you can see, like I said, as this is spinning, and it does it really, really fast. You'll pull this piston out, suck the fluid in, it comes back around, pushes it back out, and out your outlet port. Pump ratings. So we talked about the different types of pumps. One pump doesn't fit all. There's different size pumps. There's different configurations of pumps, like you just seen. But we're going to talk about the two primary ratings you have on a pump. You have a flow rating, and pumps are typically rated on how much fluid they can flow. And this is flow rating is the unit of measure is gallons per minute. So in 1 minute, how many gallons of fluid can that pump move through its outlet? And then the other rating is your pressure rating. How much pressure can that pump develop under normal operating conditions? So pressure ratings basically is how heavy duty the pump is designed as to how the pressure can produce without damaging. And this information here is provided from will come from your manufacturer, from the pump, but we're going to spend a little time talking about your flow rating. So pump ratings, I said a pump is rated in how much fluid it can move in a minute, or how many gallons it can move. So to find gallons per minute, this is the formula that we're going to use to determine how many gallons per minute we can move. So what this formula is cubic inches per revolutions times your RPM divided by 231. So this first section here, cubic inches per revolution. So what that value is the volume that is picked up for, if I follow this through one revolution, how much fluid did it actually pick up and move to the outlet? And that's measured in cubic inches. So for each revolution, this pump's going to move a given amount of fluid. RPM, revolution per minute, and that simply is just how fast this is spinning. So if it's turning 100 RPMs, so that means in 1 minute, this spins 100 times. So we're going to move this times 100. The cubic inch per revolution, we're going to move this amount of fluid for each revolution times the number of revolutions per minute. And then this 231 is just a constant. All that's doing is taking taking a cubic inch, because you're going to, once you do this part of the equation up here, you're finding out how many cubic inches of fluid you're using, or you're moving in a minute. And when you divide this by 231, you're just converting it from cubic inches to gallons. So the 231 is just a constant. So let's do an example here. So let's say this pump right here can move 6.7 cubic inches per each revolution of the rotor. So, and the motor we've got it hooked to is spinning 1,725 RPMs. So for each minute, we're going to move this times this. So let's do that. And then we divide it by 231, and that gives us a pump that has a cubic inch per revolution volume of 6.7 cubic inches, turning at 1,725 RPMs, will move 50 gallons of fluid per minute. Pump ratings, like I said earlier, they're provided by the manufacturer. So I just wanted to show you where the pump ratings come from, how you determine how much fluid flow a pump can produce. But basically, when you get a pump from a manufacturer, this information will be provided for you. So in our first slide, we talked about we were going to look at fixed displacement pump versus a variable displacement pump. Fixed displacement pump basically is what that is, a pump that has a fixed volume that it's going to pick up and flow, and it can't be changed. So this pump, no matter how fast I spin it, it's only going to move the same amount of volume each revolution. So there's no adjustment here. There's no way I can change the amount of volume that this pump can move on each revolution. And fixed displacement pumps can be vane pumps, gear pumps, or piston pumps. So each of the three configurations, they make fixed displacement pumps. The variable displacement pumps are a little different. That means for a given RPM, I can actually vary the amount of fluid that pump will flow. And you can find variable displacement pumps in vane pump configurations and piston pump configurations. So as an example, we go back to our piston pump here. Like I said, I've got the swash plate here, and it's set on an angle. So in that angle, it's moving these pistons a set amount. So if I change this angle on the swash plate, then my pistons aren't moving as far. And I can actually fix it to where this pump is not pumping very much, or I can put a large angle on the swash plate and create a larger stroke on the piston, which actually pull more fluid in and move more fluid. And so that's the difference between a fixed displacement and a variable displacement. With fixed displacement pump, I can only move a set amount of fluid per revolution, and a variable displacement pump has equipment on the inside or components on the inside that allows you to vary the amount of displacement or amount of fluid flow through each revolution of the pump. Schematic symbols. If you go back to our original design, our original symbol print that I showed you at the start of this presentation, this is a fixed displacement hydraulic pump, unidirectional. And what makes this a pump is I've got a circle here, and I've got this arrow here pointing out, or this triangle is pointing out. That tells me it's a pump. And with this being colored in or solid, that tells me this is a hydraulic pump. Here's another pump. It's a fixed displacement, bidirectional flow. So this shows that I've got a triangle pointing out, another triangle pointing out. So that tells me this pump can be spun in either direction, and it'll produce flow in either direction. And since these are solid, that tells me that these are that it is still a hydraulic pump. The third symbol I'm going to show you here is a variable displacement, unidirectional flow. So you notice I've still got my circle with the solid triangle pointing out, and then this angled arrow here. And this is a common symbol, and you'll find this symbol on several different of the schematic symbols. There's this nomenclature on several of the different types of schematic symbols as we go through this course. The angled arrow means that it is variable. So this is a unidirectional hydraulic pump, and this arrow tells me it's a variable displacement pump. And same thing here, I've got a bidirectional pump, and this arrow tells me that this bidirectional pump is variable. And then you still go back to your prime movers. So a circle with an M normally stands for a motor. So this would be attached to your pump as a prime mover. And this is a symbol for an internal combustion engine. So if we go back to our print, like I said, focusing on this area right here, I've got my a tank symbol here. So this is my reservoir where I'm pulling the fluid up. I'm going through a filter into my pump, and this symbol tells me it's a unidirectional hydraulic pump, and it's being driven by a motor. And this arrow right here even shows you the direction of rotation on that motor and pump. So we'll get into the rest of the circuit later on subsequent presentations. That kind of gives you the start. So we've kind of talked about hydraulic pumps and what they do, kind of how they're constructed, and what can cause one to fail. So 80% of the failures are caused by contamination. And what I mean by contamination is you get dirt or other types of contaminants in your hydraulic reservoir, your tank, and that dirt reservoir, you know, if it's not filtered well, maybe your filter fails and pulls that contamination into the pump and will cause erosion. It'll cause it to kind of really eat itself up, and it'll start bypassing inside, and you'll start noticing your flows, it can't produce the same amount of flow that it did before. Pressure might start dropping. So contamination is probably one of the worst things you can do to a pump. Another type of failure is aeration and cavitation. Basically, both of these is you're introducing air into the fluid stream, into the oil. The difference between aeration and cavitation is aeration is on the suction side of the pump, where you're actually drawing fluid out of the reservoir into the pump. You could have a leak there or something where it's allowing air into the stream, and as the air comes into the pump, when you start compressing it under high pressures, it makes those air bubbles implode and causes a shock wave inside the pump and damages the pump. Cavitation is also a way of introducing air bubbles, bubbles into the hydraulic oil. We use this from overspinning a pump. If you're trying to move the fluid too fast, and it creates bubbles inside the fluid, and the same thing happens with aeration. Those bubbles will implode and cause a shock wave inside the pump, and it causes the pump to heat itself up. Overpressure, 5% of failures. So this would be like I talked about with deadheading a pump. So if you try to restrict the flow of that pump to less than what that pump is capable of putting out, then you can end up with a cracked case, damaged components, gears and vanes, pistons on the inside. This will certainly destroy a pump. Other causes combine poor fluid. You know, if you don't change the fluid often enough and the additives start breaking down, defective parts, you can have something break inside the pump, just maybe a manufacturing flaw, accidental breakage, maybe over torquing a bolt and breaking a bolt, or not getting everything seated just right when you put the housing back together. That just kind of gives you a breakdown of the failures. But the worst, probably one of the worst failures you can have, and the most common, is contamination. Dirt in a hydraulic system is your enemy. So just kind of give you an idea of what you might find out in the industry. If you have any questions, please post them in the discussion board, or send me an email, or you can also call me. I'm happy to answer your questions. And now you're ready to move on to lesson 1. Good luck.